The 0-1 knapsack problem is the following. Suppose you have a knapsack with a fixed capacity, weight, or volume, and the weights of some items you can place into it. If the items have value as well as weight, what is the greatest total value that can be packed into the knapsack? To avoid learning anything, ask Google or a large language model AI to solve the problem. But remember, if you can do that, so can someone else making half your salary. Remember, don't solve problems, create solutions. If there are n items, the brute force approach is to try all 2 to the n possible subsets and determine which produces the greatest total value. But with just 100 items, this will take 2 to the 100 steps. A computer that could check 1 billion of these sets a second would take about 40 years to go through them. No, not 40. 40 trillion years to go through all of them. So we'll want a more efficient method. A key strategy for solving problems: solve a simpler problem. A key challenge for solving problems: what makes the problem simpler? We have several things we could change: the knapsack's capacity W and the number of items. Let's try to decide which makes the problem simpler. So remember, concrete doesn't hurt. Let's consider 2 problems: one where the capacity of the knapsack is lower, and one where the number of items is lower. Which one seems easier to solve? It might not be clear which is easier, but notice that if we reduce the capacity of the knapsack, we also eliminate some items as possibilities. So reducing either the number of items or the capacity of the knapsack will reduce the number of available items. So let's start with fewer items. And a useful strategy: go to extremes. Our extreme case is that we only have 1 available item, or 2, or 3. And note that as new items become available, we can simply add them to the knapsack until the total weight of all items exceeds the capacity. At that point, we have 2 choices: ignore the new item, or replace some of the items in the knapsack with the new item. So once we get to a point where we can't just stuff everything into the knapsack, we need to decide whether to replace some of the existing items with the new item. While this is easier since we have fewer items, it's still the same type of problem. We need to find a subset that can be replaced by a new item. So can we simplify the problem further? Since we've already discarded the possibility of reducing the capacity, we can never ever consider it again under any circumstances. That works in politics. But if you want to get something done, you may need to revisit discarded solutions. Suppose we keep the items, but reduce the knapsack capacity. At some point, it becomes impossible to add the new item. And it's worth remembering, a choice you can't make isn't a choice. Since the capacity of a knapsack is 11 pounds, the availability of the 12-pound object is irrelevant, so this last problem is the same as the simpler problem. This suggests a dynamic approach using a 2-way table indexed by the number of items available and also by the knapsack capacity. So suppose we have our set of weights and set of values. We'll assume the weights of the objects are in order. This isn't really necessary, but it will make things easier later on. Let d of ij be vij a, where a is a subset of the first I items, whose total weight is j or less, and whose total value vij is as great as possible. In the knapsack problem, if an item becomes available to add, we can simply add it if the total weight of all items is less than the knapsack capacity. But if the total weight exceeds the knapsack capacity, we have to decide whether to replace some existing items with a new item. This seems to require looking at all possible subsets of the existing items, which returns us to a brute force algorithm. Can we avoid this? So suppose we replace some of the current items with the new item. For example, we might have items of weights 1, 3, 5, 7, and 8. We could replace the items of weights 5 and 7 with the 12-pound item. We could write this way. But notice this is the same as adding the 12-pound item to the set consisting of the weights 1, 3, and 8. In other words, replacing existing items with a new item is the same as adding the new item to an existing set. And remember, things that do the same thing are the same thing. Now, suppose that this set is optimal, giving us the greatest possible value. If we viewed this as adding the 12-pound object to the set containing 1, 3, and 8, then 1, 3, and 8 must be optimal as well. That's because if it wasn't optimal, there'd be some other set of items that would have greater value but equal or lesser weight, and adding the 12-pound item to that set would give a knapsack of greater value but equal or lesser weight. But we assume that the set 1, 3, 8, 12 was optimal. This means that in this set 1, 3, 8, we would have had to have excluded other items weighing between 8 and 12 pounds. But the only reason for excluding them is they weren't available, or the knapsack capacity wouldn't allow their inclusion. Since the items would have been available before the 12-pound item became available, it follows that the knapsack capacity would not have allowed the other items. It's useful to remember that optimization problems often involve selecting between choices. Suppose the ith item becomes available when the capacity of the knapsack is j. If we can't just add the item, then there are two options for the optimal knapsack. We can either ignore the new item and keep the knapsack with capacity j filled with some of the first I-1 items, or add the new item to the knapsack with capacity j minus wi. Then we'll use whichever gives us the greater value. So let's see how this might work.